guess I'll just reiterate, one of the important take-home topics from differential equations is working with these spring mass problems. We will do a couple of spring mass problems in class, but you've been developing that understanding in your pre-work. So just kind of keep in mind that there are topics that are presented in the pre-works that we often don't get to in class. And that doesn't mean that they're not important. It just means that it was a topic that I felt like you could learn from the pre-work. If you feel like, hey, Charles, I watched this pre-work and I have no idea what the heck is going on, stick around tonight for office hours, or I've got office hours from 9:30 a.m. to 10:30 a.m. tomorrow. So you've got a couple of opportunities left this week to get some help on that. But just, my hope is that those pre-works aren't becoming just kind of busy work for you that you're just quickly copying down. Like if that's the case, maybe hold off on doing them and work on something else that you do feel like is worthwhile. But as you're working through those, like if you're stuck on something, please come by and get help. I would love to help you with that. Like the further you go in math, the better it is for you to try something on your own, get stuck, and then come get help on that. Because there's no way a teacher can preemptively answer all possible ways you could get stuck on a pre-work or get stuck on a topic. We try our best, but there's just no way to do that. So it's better for you to get stuck and then come by and see us for help. Okay, that's it. Let's go ahead and jump into this. I'm kind of excited because I find teaching power series solutions to be one of the most challenging topics we do in this class. But you've done it once already. And so we're coming back at it with a little bit of time has passed since you did it on the first exam. And so I'm hoping that things click a little bit more this time through. Nothing is going to change in this set of notes. Technically, we're doing them for second order ODEs as opposed to first order ODEs, but that in no way changes the difficulty of these problems or the amount of theory in these problems. We just proceed as we did before, and we're just going to get better at this topic. Let's give it a shot here. Okay. So I'm just going to run through these steps with you. Remember that what we do with power series is we guess that there's a power series solution. Okay. We take as many derivatives of that power series as we need to. We then substitute our guess and all the necessary derivatives into the original ODE. Okay. Then here are the hard parts. This, in my opinion, this is the hardest part of the power series. Okay? And the whole goal is to make use of this theorem right here that says if the power series is identically zero, don't read that as a power series. If the polynomial is always zero no matter what you plug into it, then the only way that could happen is if all the coefficients of that polynomial are zero. Right? So, folks, I don't know that people usually say this in a textbook, but it's helpful. When you think of a power series, think of an infinitely long polynomial. And if the infinitely long polynomial is always zero, you plug in 1 into it, it's 0. You plug in 2 into it, it's 0. You plug in the square root of 5 into it, it's 0. If it's 0 for all things you plug into it, then it wasn't really a special polynomial at all. It was just the equation y equals 0, which would mean that each CI has to be 0. And that's the theorem that we make use of. How do we make use of it? First of all, you simplify the summands. That can involve all sorts of rearranging. Okay, and that's case by case, problem by problem. Okay? But eventually then your goal is to align the powers and then align the indices. That hopefully rings a little bit of a bell. We're going to get some more practice with it tonight. And then you try to write the entire equation in this form. So that means you've joined it all together into one summand, if possible. Once you've done so, you can make use of that theorem up above, and you go ahead and solve for the highest expression involving n, and you're creating what's called a recursion formula. Okay? You will always be able to do this if there's a power series solution to this problem. You'll always be able to do that. Sometimes you might be able to form a generating function for that. Sometimes you get to the end and your power series is recognizable. Oh, I know that power series. It's the power series for e to the x. Or, oh, look, there's the power series for the sine of 5x or something like that. That's wonderful, and sometimes that will happen. Okay? but these last two are not guarantees. Okay? You must find the radius of convergence. Usually you use the ratio test on that. But to be honest, this gets into some other theory that goes with power series, and I will give you a couple paragraphs at the end of this handout that we're not going to talk about. I'll just direct them to you, direct you to them. Okay. So I like this next example because we won't really be able to come up with a non-recursive formula for it. We won't be able to write out the solution to this in terms of ordinary functions. And it has a lot of applications. So this is called Airy's equation here. And this is, you know, when we did the power series solutions in the first unit, you were able to quickly check them because you already knew how to find the solution by some other means. This is the first one that we do where I do know of another way, but it's kind of not where we want to go with this class. There's not a good way to come up with a solution to this differential equation. Why can't I use the techniques we're currently using for this, folks? Characteristic equation, method of undetermined coefficients. Why will that not work here? Yeah, we don't have constant coefficient functions here. And in some cases, there are other techniques that we can use, you know, other classification. I know of no other way to solve this other than with a power series solution. So this feels like a more realistic scenario. So let's give it a shot. And I might be in trouble, folks. I'm sorry, folks. We're going to have to pause this. I got to go get my stylus. I'm so sorry. Let's do this. Let's have you as a group try to start on number 5 here while I run and grab that. Okay, so try to start number 5, and I'll be right back. All right, folks, I'm sorry about that. Let's put what you're working on the back burner and jump back to question number 3 here. So I'll give you some more time on that one here in a little bit. So what do we do here? We first suppose, or we guess, however you want to say that, guess that y equals the sum from k equals 0 to infinity of c sub k x to the k solves the ODE. Okay. Where do we correct the fact that this is just a guess? Where in that list of steps do we actually fix the fact that we just guessed that there was a solution here? That's a good insight. Like that finds those, like the goal here once we've made this guess is to find all those c sub k's. That's true. The radius of convergence is when you show that this actually works. So that's why that finding the radius of convergence when it's possible is so important. Okay. All right, we take the first derivative here and we get the sum from k equals 1 to infinity of c sub k, k, x to the k minus 1. And we take the second derivative, the sum from k equals 2 to infinity of c sub k, k times k minus 1, x to the k minus 2. And I think the first few times you did this was kind of a strange operation, but I think we should be feeling a little bit more comfortable with taking these derivatives of our supposed series. Does that help a little bit, folks? We feeling a little more comfortable with this process? I guess I should ask it the other way. Is anyone feeling not sure what we're doing here? Okay. So then we're going to plug all 3 of these back into the original ODE, or any that are relevant into the original ODE. So I've got the sum from k equals 2 to infinity of c sub k, k, k minus 1, x to the k minus 2. And all of that was our y double prime, right?
and then we'll subtract from that series x times the sum from k equals 0 to infinity c sub k x to the k equals 0, where this component right here was our y. And I had some of you ask, and I didn't do the best of job my first time through with this, explaining it. I had some of you ask about, hey, Charles, aren't these, like, why did we write it this way? Why did we write this way? Especially if when you go to align powers, you seem to put things right back the way they were. And it's for these non-constant coefficient cases where that's more important. Okay? So now we'll notice that the first thing I'm going to do is go ahead and simplify the summons. And I said that part is kind of problem dependent. Okay? If there was a sign of x here, folks, what could you do if there was a sign of x sitting here?
Like a switch and pull up the negative sign?
An SINE or cosine of x or tangent of x sitting here. So, well, I don't know about tangent of x. You could give the power series representation for a sine of x, and then you could combine the two series together. We don't do that often. I don't know if you've ever multiplied two series together, two infinite series multiplied together. Okay, but you could do it. There is a bookkeeping way to keep track of that to at least generate some terms. Okay, so pointing that out to you because that's how versatile this method is. Even if we don't do the problems, the messiest of problems, this will help with those messy problems. Okay, and that's why issues like radius of convergence, right? You know, knowing how to generate a few terms of a series, it's so important, even if you're not going to have such nicely cooked up problems as these in the real world. And even though you get, you know, ChatGPT or Mathematica or some sort of math lab, some sort of system that will solve it for you, you still need to have a good working understanding of them. Okay, so let's go ahead and I'm going to leave this first piece alone. There's a little bit of redundant writing here. Leaving that first piece alone, c sub k, k minus 1, x to the k minus 2. And then I'm going to bring in that power of x right there, so that'd be the sum from, in fact, yeah, that's fine. We'll just do that. K equals 0 to infinity of c sub k, x to the k plus 1. Where did that plus 1 come from, folks? Yeah, we brought in another power of x. When we do x times x to the k, we get x to the k plus 1. Everyone okay with that? So then, now that we've combined these summons a little bit, what's our next goal? That's the last one, in my opinion. We align the powers first. And this is sort of a Rubik's Cube. You don't want to undo the work you do. So my recommendation is to first align the powers, then align the indices. Sometimes if you go in the opposite order, things will still work out. Sometimes if you go in the opposite order, you might end up undoing some of the work you've already done. Okay. So let's go ahead and align the powers here. Notice that the first term starts at x to the 0th power, but this second series starts at x to the 1st power. So remember, and this is the part that this is so abstract when you're writing it in series. What are we trying to do right now, folks? We're trying to do one of the earliest math skills you learned. Combine like terms. Right? That's what we're trying to do. We're trying to combine like terms here. But that's easier said than done with these infinitely long polynomials. Okay? So this infinitely long polynomial has a constant term. And then all the other terms follow. This infinitely long polynomial doesn't have a constant term. It started at x to the 1st power. So I'm going to peel off the constant term from this polynomial because it has a term that the other one doesn't. Okay? We didn't get all that much practice with that our first time through. Does that make sense to everybody? Would anyone like to talk about that further? Because I can draw up a polynomial up here which might make it way more concrete. Does anyone want to go through that further?
Steve Wolf says he wants to see it a little bit further. Steve didn't, but I'm going to pretend he did.
I did.
Thank you. So if I have this polynomial, 3 plus x plus 5x squared plus 7x cubed plus yada, and I have this polynomial, 2x plus 4x squared plus 6x cubed plus 8x to the fourth plus yada, I'm trying to combine together these two infinitely long polynomials, right? And so what I'd like to do is combine like terms, right? But I can't just combine this with this and this with this because they're not like terms. Everyone see that? So what I'm going to do is I'm going to peel off that constant term. So now I scoot everything over and now the powers are aligned. And I think it's good to have, like, whenever you get stuck working with sums, folks, just remember that they are a shortcut notation that math people invented because after they spent a lot of time writing out expressions very far, they got tired of it, and so they condensed it. Whenever you get stuck with sums, go back to writing it out in a little bit of an expanded form off to the side, just for practice. Okay? So I see this polynomial right here starts with a constant when k is 2. So I'm going to pull off c sub 2 times 2 minus 1, x to the 2 minus 2, and then add to it the rest of that polynomial. And please write small, folks, because I'm going to probably have to a couple times here cheat and make my writing smaller. I'm sorry. Okay. Does everyone see that now? First of all, do you see what I did here? This infinitely long polynomial started with k equals 2, and it was a constant term. So I just plugged in the k equals 2 term and peeled it off from that infinitely long polynomial, and now we're at k equals 3. Okay. I'm looking for some feedback here, folks, because this is, I know the first time I teach this topic, half the students are pretty lost as to what I'm doing with it. But now we're doing it our second time through, and and you've already taken a test on, and this showed up as a question on your exam. So I feel like now's a great time to say, Charles, I've been struggling with this. I've got a question on this step right here. Yeah, JP.
I guess my question is, why did you try doing it like, so the third term is k to third, right? K is equal to 3.
So now this series starts at k equals 3,
Right.
and it would give me the linear x. So when I plug in a 3 here, we got x to the first power, right?
Mm-hmm.
When I plug in a 0 here, I've got x to the first power. So what have I done? I've aligned the powers. So it's like, again, our goal is to combine like terms, but we're doing it in this very abstract way. So the first thing would be to get the powers aligned. Now, if I'm just considering the polynomial from here onwards, and this polynomial from here onwards, they both have the same, the first term is to the first, whatever term you're calling it, this is to the first power, this is to the first power. This is to the second, this is to the second. We're getting closer to be able to adding like terms.
Right.
Yep. Great questions.
There's one thing I don't get.
Uh-huh.
Why do we use that series for our initial series and work off of that?
What's that?
Why do we choose the series we choose, the c to k, x to the k, for our initial series and start from there?
Well, one answer is that this starts with an x to the first power. I don't want to add in an arbitrary, like some, I don't want to put a plus, I don't want to add 7 to this, because now I've changed it.
No, yeah, I get that. Like, why is that what we decided to use? Like, are there other series we could have used to do the same result here?
Why are we doing a power series? Because believe it or not, power series are the best ones to work with. They're the easiest ones. There are other types of series that are all kind of variations of power series. Laurent series, Frobenius series. There's all sorts of other series that we could do. But the simplest, I mean, what are power series? polynomials. All other series are more complicated expressions than that. So this is our power series method. Yeah. How's that work?
I think, yeah, it kind of makes a little sense.
Yeah. Okay, so folks, I'm getting closer to be able to add like terms, except what? If I started out calling this term 20, this term 21, this term 22, and I started out calling this term 98, 99, 100, I need to be referencing them by the same index before I can just say combine like terms. So the next step is to combine the indices. So we can see that so we're going to shift the indices one way or the other, and it does not matter. You just have to be consistent. Okay. Additionally, this is not my final indexing of this power series. When I get to the very end, we start generating all of the constants afresh. Okay. So I think I'm going to bring everything down to actually, I think I'm going to go ahead and add 3 to this one, so then our indices are aligned. Okay, it's probably arbitrary, so that's just what I'm going to do. Okay, so cleaning this up, we've got 2 c sub 2 plus the sum from k equals 3 to infinity c sub k, k minus 1, x to the k minus 2. I left that index alone, and now I'm going to shift the indices here. So I'm going to do a substitution, which I usually don't write out. You saw me try to fumble through that my first time through. So the net result is we just go ahead and add 3 here and compensate by subtracting 3 here. So this change here was just shifting the indices. If you ever want to do it with substitutions, come by and see me where I'm not under pressure in front of 20 people, and I'll do a little bit better job. Okay, but really you're just doing a substitution in how you're labeling these indexes, right? Again, the idea is if for whatever reason we started calling this term 5, 6, 7, and we're calling this term 3, 4, 5, we want to pick a common way of enumerating them. That's the separating of the indices. Or that's the aligning of the indices. Okay. So now look at this, folks. Now we truly have like terms. When k is, the first term is when k is 3, and that agrees for both of these. And when I plug in 3 into both of them, we've got x to the first power. So these truly are like terms. So now adding like terms is just combining the series together. That's all that work has been, is just to combine so we can add like terms. So this gives me 2c2 plus the sum from k equals 3 to infinity of c sub k times k minus 1 minus c sub k minus 3 all times x to the k minus 2 is equal to 0. We've combined like terms there. How much room do I have? I think I can make it. I'm going to make it a little smaller. Okay. So my hope is that, because this isn't our first rodeo, these steps are feeling like they're still difficult. I'm not saying these are easy steps, but we know which step is coming up. We align the powers, we align the indices, and now what do we get to make use of? We now get to make use of this theorem right here that says if a polynomial is identically 0 regardless of what x is, then each of the constants had to be 0. So coming down here, we'll say that C2 has to equal 0. Okay. And further, C sub k times k minus 1 minus C sub k minus 3. And folks, be careful here, especially if your handwriting's kind of like mine. At some point, your subscripts start to stop looking like subscripts, so just watch out for that. And we're going to solve for the highest C sub k term here. Which one's the highest C sub k term in my renumbering of things? C sub k. If you'd renumbered it differently, maybe your highest term is C sub k plus 2. Doesn't matter. You solve for whatever one is highest. Okay? In terms of previous ones. That's what we call a recursive formula. That word recursive sounds a little complicated. It just means to give the next step or steps, you have to know some of the prior steps. Okay? So if I solve this for C sub k, I would have k times k minus 1 C sub k is equal to C sub k minus 3, or that C sub k is equal to C sub k minus 3 all over k times k minus 1. Okay. And this is what we were after. And if this has a power series solution, these two things, if this has a power series solution, you will always be able to come up with this this recursive formula. Yes, all right.
So all the coefficients are 0. Why don't we say C sub k and C sub k minus 3 are 0?
Because we still need to know how they're all interrelated to each other. Like that's what we're. So let me say it like this. These will not be. These C sub k's will not be the eventual C sub k's that we give in our solution. That these were like we said, okay, suppose like this is our solution here, just this one. And this enumeration, like in enumerating things like we've renamed and whatever. So I'm not saying this C sub k is the same as this C sub k right here, okay? Because we obtain this by combining this into a single series. So not for our original guess at the series, am I saying all the C sub k's are 0. I'm saying once you've combined y with y double prime, you get a series where each of the constants has to be 0. And that should actually make sense, right? Because what's this power series? The power series solution, when I combine it with its second derivative after multiplying by x, is supposed to give me 0. Right? So when I combine all these terms together, I'm supposed to get 0. That doesn't mean that when I started out with y, that all of the terms are 0. It was after I combined them together. How's that?
But if power series equals 0, I thought all the coefficients.
Okay. So our power series doesn't equal 0. It doesn't say this equals 0. When we combine our power series with our power series second derivative after multiplying our power series by x, it equals 0. Does that make sense? So for example, sine of x does not equal 0 for all x, and neither does its power series, right? But when I take two derivatives of sine of x, then when I combine y double prime plus y, I get 0, and the series for these, like again, the series for sine of x doesn't equal 0. The series for y, so the series for y doesn't equal 0 for all coefficients. The series for y double prime doesn't equal 0 for all coefficients. But when I've combined them together into a single power series, then all of their coefficients would have to add to be 0. And that's after you've done the derivatives and substituted it all into we're not just talking about this function, we're talking about what we subbed into the ODE. Yeah. Great. Okay, so what do we do now? We've got our recursive formula at long last, 30 minutes in. What do we do next?
Yes, we get more terms.
We start generating the terms. Okay? This is second order. So I said there were no differences, and there really aren't, but this is second order. So we're going to let C0 equal C0. We'll let C1 equal C1. And then we already know that C2 is equal to 0. And then what's C sub 3 going to be? C sub 3 will be C sub 0 all over 3 times 3 minus 1. Or C sub 0 all over 3 times 2. As a reminder, folks, because sometimes you're looking for a pattern here, the rule of thumb is not to simplify multiplication or division, because that'll make it harder to see things like powers and factorials if you've been cleaning them up as you go. In this case, we're not going to come up with a non-recursive formula, but we should still act as if we were.
So if you get the C for C2 equals 0, anything before C2 will just be.
No, that's a good question. I didn't make both of these constant because C2 is 0. I made both of these constants because we're always going to be generating new terms in terms of prior terms. And we get these terms because we've centered this power series at 0, and we'd be presumably given initial conditions for when the function is 0, for the value of the function at time equals 0, and the value of the function's derivative at time equals 0. Those are the initial remember, for a second order, we need how many initial conditions? 2, and those are the 2 initial conditions. Yeah.
So it's more based off of the
Order.
order.
Mm-hmm.
Okay, so if it was 3, it would be like C0 equals C0, C1 equals C1, and then C3 equals C3.
C2 equals C2.
C, yeah.
If we had a third order,
Yeah.
yes. And maybe, and I think we still want to keep it at 0 because we start our power series at 0, but maybe you would rename them at the end. Mm-hmm. All right, so then C4 would be C1 all over 4 times 3. And then C5 is equal to C2 all over 5 times 4. But what was C0? Or excuse me, what was C2? I said it. I didn't mean to. Which equals 0. And in fact, this series has the property that every third coefficient would be 0 here. Okay. Let's keep going. Let's keep generating a few more terms. C sub 6 would be C sub 3 all over 6 times 5, which is equal to, we already know what C sub 3 is, so that would be 1 over 6 times 5 times C0 over 3 times 2. Eric, where did I get that from? C3 is C0 over 3 times 2, and so I just pulled that out. Exactly. So this is that recursive formula, and this is true. Like, once you know earlier coefficients, because of the way we've set this up, we'll be able to find future coefficients. Yeah, JP.
How far should we continue with this?
Yeah, far enough. That's not a good answer. We want to go far enough that you can start to predict what the next thing will be without actually writing it out. Okay, so let's go just a little bit further here. I think I'd like to go to about C8. If I go to C7, I get C4 all over 7 times 6, which is equal to 1 over 7 times 6 times C1 over 4 times 3. And that's all the room I've got. And if I go just a little bit further, let's do C8, and then we'll C9, and we'll call it good after that. Okay. So if I go to C8, what's C8 going to be? Well, it's going to be, by our recursive formula, it's going to be C sub 5 all over 8 times 7. It's a subscript there. But what's C sub 5? So that's just equal to 0. Again, we said every third term will be 0 here. Okay? So let's just see if we can guess what the next term is. And if that's the case, then I feel like you've gone out far enough. So JP asked, and it's a good question, how far should you go? And I think I don't need the recursive formula anymore to generate the next term. I think I can kind of guess what it is. That means I've probably gone far enough. So I would say that C sub 9 would be, let's look at our pattern here. C sub 1 was C sub 1. C sub 4 was C sub 1 over 4 times 3. C sub 0 was C sub 0. C sub 3 was this. Well, I'm looking at these three together. This, and this. And so I think I can come up with c sub 9 as 1 over 9 times 8, skip 2, or skip 1, 1 over 6 times 5, 1 over 3 times 2, c sub 0. So I think I've gone far enough to see the pattern. Okay. How are we doing, folks? Now, this is where, again, in these directions, in these directions I said, if possible, find a non-recursive formula. I can't really find a non-recursive formula for that. Okay? Which means I definitely won't be able to write this in terms of elementary functions. That's really interesting, right? We are solving a problem that we can solve by no other means. Like there's not, I mean, I guess you could give a name to this solution, and I guess people do, but there's not some combination of sines and e's and square roots and natural logs that will give me the solution to this equation. That doesn't mean it doesn't exist, though. Existence uniqueness theorem guarantees this exists. It just can't be written in a nice way. The same thing was true in Calc 2. There were some integrals that you can't evaluate in a nice way, even though you know an answer exists. And those were the ones that were often represented with series solutions, because that was the best way to do it. Okay. So now I think I can go ahead and start grouping some of these together. So I think we've got our solution is y sub x is equal to, let's group all the ones that have C0 in it. Okay. So it would be C0 x to the 0 plus C0 over 3 times 2 x to the third plus C0 all over 3, where was the other C0? 6 times 5, 3 times 2, x to the fifth, and then I'll put plus dot dot dot. Okay, we could generate more terms if we wanted, and that becomes how accurate do you want your solution to be as far as a numerical approximation goes. Okay. Plus C1 x to the first power plus C1 over 4 times 3 x to the fourth power plus C1 over 7 times 6 times 4 times 3 all over x to the, add 3 to that, 7th power plus dot 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 plus a bunch of 0 terms. Okay. So if I wanted to, I could kind of reconfigure this by pulling out the C0. So I'd have C sub 0 times 1 plus 1 over 6x cubed plus, I need a hand here, folks. We're going to do 6 times 5 times 3 times 2. So
X to the 6th, not X to the 5th.
this should be x to the 6th. That's a great catch there. Who said that? Yeah, Harrison, that should have been x to the 6th there. Let's put that in red for an embarrassing mistake. Yes. No, not embarrassing. We make mistakes all the time. How's that? Good. 180, I buy it. Plus 1 over 180 x to the 6th plus yada. Plus C1 times x plus 1/12 x to the 4th plus, I don't know, 42 times 12. 420 and 24. Is that 244? Help me out, folks. I need a hand. 504? Thank you. Plus 1 over, I wasn't close at all. 504 x to the 7th plus dot dot dot. Okay? And this is the solution to this differential equation. Here I've only written out the first 1, 2, 3, 4, 5, 6 non-trivial terms. What are the trivial terms?
0.
The terms that are 0, right? Every third term in this were 0. So, folks, on your homework for this, I'll ask you to write out the first 6 non-trivial terms. There you're not giving the full answer, you're giving a approximation to the solution. Okay? One thing I don't get into in this class, I think you've probably had enough, is like if you only go to the first 6 terms, how accurate are you? And at the place you centered this at, you're 100% accurate, and as you go further out, away from where you've centered it at, you're less accurate. What if you wanted to be more accurate? You just generate more terms. This is, to me, probably the most realistic differential equation we've solved in this class. This Aries equation here. Because this is what happens in the real world. Seldom do your differential equations match a perfect form exactly like they taught you in your class. And so here is an approximation method for giving us whatever degree of accuracy you want, but you generate solutions to this. All right, I want to do the quickest of comments on this. The original ODE had this piece of x term. Actually, I think I usually label that as a2 of x usually, so let's do that. This a2 of x here was what? It's just the constant 1, right? The constant coefficient function. And this a naught of x was just equal to x. From our existence uniqueness theorem for this unit, we said that as long as these coefficient functions were all continuous and the leading coefficient function wasn't 0, and I guess if we had a forcing function here, as long as all those functions were continuous, we were guaranteed a solution, right? That actually answers the question about what would our radius of convergence be. If you're curious about that, there's a conversation at the very end of this handout that goes into that. Okay? So notice here, because I don't have a nice single series, it would be hard for me to generate the radius of convergence by doing my ratio test, because I don't actually have a series to take the ratio test on. Okay? But I know that the radius of convergence here is infinity because the original coefficient functions were always continuous. Yes?
Would something like this be on the test where we'd have to find the radius of conversion? Or convergence?
Not on this one.
No.
On the one below, perhaps.
Okay.
Yeah. Okay. How we doing, folks? All right, let's do it again. Now, first of all, without doing power series, in your tables, I want you to solve this equation in 3 minutes without doing power series. In your groups, solve this equation in 3 minutes.
Why you telling me this? You know, like, ignored you half the time, right? Cool. I don't really like your attitude, Buster. Really grinding my marbles.
do know what to, okay, I know what to spur tonight.
Forest through the trees. Forest through the trees here.
I cannot believe I just did that.
Okay, folks.
Am I wrong?
I got y double prime plus 9y equals 0. My characteristic equation was r squared plus 9. Careful, a common mistake is to write that your characteristic equation is r squared plus r. Right? So you don't get that wrong if you say my guess is y equals e to the rt and do all the work that we did. Remember that when we first introduced this idea, there were about 3 lines of work that went between the two to prevent that error from happening. So just be careful there. So I got r squared plus 9. We okay with that? Which has roots plus or minus 3i. Checking in. So then in general, when I have a complex solution, it generates these two solutions here. But in this case, these were strictly imaginary roots. And so the e, we'd have e to the 0t. If you had jumped straight from here to here, I'm perfectly fine with that. But sometimes I forget that, so I went ahead and wrote that. Yes?
On the board, you just have 30.
Oh, sorry. There you go. Thank you. Good catch. How we doing, friends? Like, this is I'm hoping this is a good starting point for this problem. We already know what the answer is supposed to be before we go do it. Okay? Unlike our Airy's equation, right? Airy's equation, we had no idea what the answer was going to be. And in fact, there is no other way to do that problem except for power series, at least in this class. Okay? There's no other techniques that would work there. Because why? The answer to Airy's equation is not an equation that you can write out in terms of elementary functions. This isn't equal to some e to the x with a square root in it, with a sine in it, with a natural log in it. There's no other way to write out this solution. Okay. In general, I would say that if you go to solve a series with power series notation and you get a nice answer, it usually means that another technique would have worked with it. Okay? But we're trying to learn those techniques here. Okay? All right. So here we go. Well, actually, let's let you all try this. Yeah, let's have you all try this. There's a hyperlink solution there. We'll take 15 minutes. Try to solve this in your groups. Work together. Yeah, we'll have you join Nick here. So what's our guess here? Y equals sum from k equals 0, c sub k, x to the k. There you go. And then we take 2 derivatives of that. JP, how we doing here? Good. That's our guess at y. And that would be y prime. Good. Okay. Stephen, how we doing here? What? You got your y prime, your y double prime. You've already plugged them in. You are rocking and rolling. Steve Wolf, how we doing here? Rocking and rolling.
I love him so much I can't get to it.
Oh, when I said do it in 3 minutes? That's ambitious. Yeah, without using power series. Patrick, how we doing here? So you take the 2 derivatives. Be sure you set that equal to 0, right? Because the whole kit and caboodle comes down to saying, oh, this whole thing is set to 0. So that should be equal to 0 there and equal to 0 there.
It's at the beginning.
Very good. David, how we doing there? I like those remarks. Is that a remarkable? Or something like it? I like those. Yeah.
And then one of them's Oilers
All right, how we doing here?
That doesn't even change at all. It's just easy.
Honestly, I don't know. Because in trying to get the reverse formula,
Nick, how we doing here?
You can't just put that in.
Great. We plugged them in. So aligning powers isn't so hard here, is it? In this problem, aligning the powers isn't too bad. Rowan, how we doing here? Plugging away? Alex? We're doing
notebook? Because you've done like recent paper.
Taking the two derivatives, good. Plugged in.
I mean,
good.
like, have it.
All right, we're plugging them.
I was like, don't feel like I do.
Eric, how you doing?
Probably just felt like a random problem.
See, the nice thing about doing this a second time is like you already know the steps. Now it's being
That's what
now
I was
it's
thinking. I was like, you brought that.
actually performing. That you're focusing on. Jacob, how you doing?
I'm raw dog eggs.
So why do you say that? With this first one, when k is 2, what's the power on x? In this case, we got lucky. The powers are, and in fact, if there's no, it's worth saying, if there's no like x being multiplied to one of those, or x squared or something like that, then the powers will actually already come out of the line, which was, some people said like, hey, why did we do that step earlier on? Because if I give you too straightforward of a problem, there's no lining of the powers that has to happen. Cool. Powers and indices are
Charles?
yeah.
Before you run away from me,
Mhm.
is it somewhat
Yeah,
good?
but then you'll have,
So you get your
n+2 and then n+1.
So then you get your second derivative, yes, and then yes, and the powers were already aligned, so then you had to shift the indices, and there I'm not sure. This index should have been at 2 though, remember?
Oh, okay.
So that would have started at 2, which means you're not ready to combine those two into a single expression yet. Colton, how we doing over here?
B when I lie. B when I lie for attention. Have a heart attack.
Nick, how we doing? Or I mean, Harrison, how we doing here? Generating some terms? Succeeds? Yes.
That was
yes.
pretty good.
Succeeds.
That was pretty good.
See, yes.
Sorry, I did attention.
Anna, how we doing here? Plugging away? Good. I know, I'm the only one for emphasizing tonight. Not quite there. Good. Cliff, how we doing? Or, I mean, sorry.
Added to each of these k's is k plus 2, k plus 2 times k plus 1.
Over powers are, yeah, m0 and then put it under some and then just like that's it out.
So just a reminder, folks, even though this one does come out to a nice function, you're still going to have to group your series into how many parts for this second order power series? Into 2, right? Because you're going to have some that are all in terms of C0 and some that are all in terms of C1. I'll be right there. Carol, yes? Oh, no question? I'm sorry? My bad. Carol.
Multiply everything by 9 or how much?
No, so that 9 should have been distributed in earlier before you combine them into a single term. There, yeah, and then go ahead and erase that. And then that 9 would only be applied to the second order. Yep, yeah.
What do you mean you've never?
So that step wasn't the most clear because it's different for every problem. But that's where I was saying
Where's the 9, bro?
simplify the sums. Meaning get them both, write them so they are actually sums before then you start peeling anything off or rearranging. Yeah.
Where the fuck did you even?
Oh, so like that's fine.
I hate you.
Yep. Good. Good insight.
And that's gonna be a negative 2.
Okay, I think I got it for C1. Now I should
Yeah, that's what I figured. I was like, bro, you forgot the most important part.
About 4.
So Patrick, I would recommend keeping that as not 81, but as 9 squared, or 9 squared. Or you could do, okay, I see, yeah. Negative 9 times 9 or whatever. Because that'll help you writing it in powers later.
I think something is wrong.
I got that part.
I went from here.
I think I got it right. Wait.
That's okay, yeah. So you skip, and so now, but nothing wrong with that. So here you would think of, like when you go to generate CISA 2, in your mind you would say, oh, if I generate CISA 2, K is 0, and you plug in 0 for all those. Here, you're generating CISA K, and that's your second term, so you can plug in 2 for all those, and those should agree with each other. So it doesn't matter. Yep. Yep. So that's where at the end of the day, if you had, when you shifted indices, you know, you chose to align them all in terms of one, maybe somebody else chose to align them all in terms of the other one, or maybe some third person said, I'm going to start all my series at 100 for whatever reason. They would still then, at this point, start generating the same terms.
So, would this then, would this be right for these, for season 0 and season 1?
You're really
Because
Zero, no.
it would be -9.
Because you said CISA 0 is CISA 0, so you're in the process of generating C2 and C3 at this point.
Yes, well, I meant like for the two different ones. You have the one for
Oh.
this, you have the one for that.
Zero.
Because,
Like
I mean, pattern
zero
looks
looks
like
like
it's
it's
-9.
Part of it, it makes
one is like
Um,
for one side.
Yeah, and this is where you may want to use the fact that you know where this one's supposed to go. We're trying to get to sines and cosines. I would keep those as -9, either -9 to the k.
It's the last day. And I'm
K
like,
starts at 0, or -9 to
it's like,
the
wait, where'd you get that? I was like, oh, that's how.
K plus 1.
You're at K plus 2
K
by.
plus, yeah, so you get to the k plus k.
They let me do it too.
I think that one should start at 2.
on your
I don't know.
back.
So
Maybe I
so there's C2,
English best.
and there's C4,
Yeah.
which I would rewrite C4 in terms of C0.
I did, right here.
Oh, my apologies.
Yeah, that's what I was
I got
trying to
most
say.
of
That's why I had -9 to the
Probably.
K minus 2.
Oh, I get it because those equal sine and cosine. Oh, I get it. Series, I get it.
So I agree with the denominator there. I think you have an easier time to get out of series.
That's news to me.
Yeah, when K is
I'm just
4.
thinking about it because, like, you know how cosine is odd.
Oh, I see what you mean.
There's no reason to put sine
Yeah.
or something.
That's why I don't know if I just did something.
So
perhaps.
here's where you want to be a little
Yeah,
careful
they
here.
just equal it. It's like, wait a
What are you
minute,
letting
this
state
equals
be in this
cosine.
part? Like, you're going to C0 be
So
C0.
that means I'm supposed to
C1
get
is
over
C1.
for
Now you're generating C2.
That's what I'm thinking.
Yeah.
And so
That
that
was
was
making
negative
cosine.
1 was 2.
Correct.
3, 4,
Pick it up. I would get a cosine. I'd be
So when
I get it.
I
I
was
really-
student, it just be,
I decided.
Yeah.
I decided.
This is Euler's formula.
Euler's formula.
Right side.
Something's going no idea.
Oh, that's right, though, because then it would be B, because it was,
No.
K was, or C was 2.
It's -9 to
Yeah.
Probably some series that I might
One of them is
No, there's
Oh, I see
the other
it.
is some would be not.
I just can make it.
So I think the
I would just write that as negative, so I wouldn't try to be generating terms. I would write that as -2 to the, I would write that as negative 9 to the second power.
But times 1 doesn't get
Oh.
Right? Because that's what it is.
Yeah.
And don't work, get a couple more terms before you try to generate again. Yeah.
Okay.
One of them is n minus 1 factorial.
Yes.
I have. See the first has n minus 1 factorial.
No, you know, I think that'll work just fine, what you wrote. I think what you wrote is just fine. I'm just a little bit. Yeah.
Okay.
But
But
pull it out in front.
then again, though, why did you say
necessary to have a technical.
C0 is C0, C1 is C1, so this would be 4K.
Since the powers of 9 are like
This would be 4K.
Well, yeah. You could,
Yeah.
but if this one equals 2, then the 9 that goes to 1, then that would be this. Like, that's what we like this.
like you can group like
That's true, but this is for
five
your K
powers
equals
of
4.
nine.
Oh,
Right.
but if my K was, yeah, but it has to be of
Show up on our
You have to multiply this one.
You know what I think?
and then it turns.
I think.
This starts with 3.
I'm not a fan of these series, man. I'm really grinding my gears.
I'm in 6.
Wait,
because these were because these resemble the cosine function. So you know the power series is cosine.
Looks like you're wrong.
Function. Literally, I think it's like
I can't even pronounce it.
this one is.
That's hard.
I have to think about it. But it's like -1 over K. Pretty
Get a
sure.
bigger whiteboard in your pocket.
Pretty sure that's
All right, folks. I know that's not enough time to work this problem, but I wanna give you a break here. So let's just run through this one all together. You have the. I don't know. Do you like those? I think they're the coolest thing. That you just have a solution right there. You can always pull up. Do you like having those QR codes? Or they just kind of.
Oh, yeah.
Okay.
Yeah.
I'll keep doing them. So you've got a QR code. You just hold your phone over it. You can see the solution. Okay? It pulls this guy up. I went ahead and guessed that the solution was a power series. What do I eventually have to do with these problems if you're guessing that?
Converging.
You eventually have to justify it with some statement about the convergence of the series. I took two derivatives. We plugged it in, and I think everyone did fine with this. We okay with that? Here I'm using n's instead of k's. Notice that because this was constant coefficients, aligning the powers was already done. And a lot of you were asking me questions about this the first time through when we did it way back at the beginning, and you're like, well, why did we do all the adjusting of the powers when we took the derivatives if we just align the powers back and everything works out? So it has to do with when we have non-constant coefficients, that's where that would be more work. Okay? But in this case, the powers were already aligned, and in my case, I chose to put all the indices to 2. Another good choice would be to put all the indices to 0. Another legal choice would make them all start at 87, but that's not a smart, not a helpful choice, right? So starting them all at 2 or starting them all at 0, either way. Okay. So then at long last, look at, when n is 2, that's next to the 0. When n is 2, that's next to the 0. We've got like terms that we can just combine into a single series. Okay. So then, not for our original series, y, but for this combined series, we can now conclude that each of the coefficients for this combined series has to be 0. Okay. And I was able to solve for c sub n. Now notice this, folks. Here, because I put all of my terms in terms of 2, I think that this is what I ended up with. If you would put them all in terms of 0, I think you would have c of n plus 2 here, and c0, like everything would just be shifted. We would agree with one another just through a shifted index. Okay. All right, so then I let c0 be c0, c1 be c1. We okay with that? Oh, so do you remember that when we did it for first order, we always let C0 be C0? So this is second order.
Okay.
So so like, you'll always be able to put everything in terms of a pair of constants, not just one constant. Okay. And that's related to the fact that basically a second order ODE, regardless of how you get there, there's some sort of notion of integrating twice to get to the solution, and each integral giving a constant is how I would think about that. Okay. So this is true for any second order. If we were doing a third order, we'd let C0 be C0, C1 be C1, and C2 be C2. And then we proceed. Any other questions about that, folks? Because that is new. I said there was nothing new, and that was sort of a lie, because this part's a little different for second order. Then I started generating new ones in terms of old. So here I can generate C sub 2, and I wrote it this way, and I generated C sub 3, and C sub 4, and C sub 5, and I started to see a pattern here. Okay? In all cases in the denominator, we started getting the factorials, and we have powers of 9 up above there. Okay? So I went ahead and wrote out a couple more terms. Like I was able to get this term without actually computing it because I noticed the pattern. Okay? And then this part is also new. I guess I shouldn't have been so quick to say. I've got a bunch of terms that all had C0, so I grouped them all together. And I had a bunch of terms that had C1, and so I grouped them all together. Which, by the way, folks, if you're really being pedantic here, we have taken that property out on loan. You're actually not allowed to just group terms of series however you want unless you already know that they converge. So that's especially why at the end we need to prove convergence. But then look at this. I think now, so this somebody had a great question about the index here. It wasn't until I got these two terms, so Harrison, this is kind of along your lines of your question. Once I got this set of terms and this set of terms, then I started to come up with a non-recursive formula for them. And in terms of, yeah, I know this is this is 0th term, 1st term, 2nd term, 3rd term, 4th term, 5th term, like they alternate. When I've regrouped them, I'm going to re-enumerate one more time. So in this grouping, this is 0, 1, 2. In this grouping, this is 0, 1, 2. So Harrison, that was what we were kind of stuck on. We hadn't regrouped them.
Yeah, I'm looking at that now. I see it.
And so then I can recognize that as that series there, and that as that series there. Now, careful here, folks. This is -9 to the n. This is x to the 2n. I'm wanting to combine those together in one exponent, so I rewrote this as 3 to the 2n. Right? I wrote so there's the -1 to the n. There's the 3 to the 2n that then gets collected here, so now I've got 3x to the 2n. Okay, so I want to backtrack just a little bit. In the real world, you ask a computer to do part of this, but you need to know what the computer's doing. In the real world, you ask a computer to do this, the computer will generate these coefficients for you. You need to know what to do with them. Well, we can arrange them like this. And in the real world, for most problems you deal with, most is something I guess I'm just speculating at, this is as far as you could go. I would say that most problems don't fall out nicely. And this is as far as you can go. And you know, if you want to be more accurate, you just generate more terms, but you usually, and usually is a vague word here, you usually won't be able to find a pattern that generates them non-recursively. If you can, it's your lucky day. Congrats. Okay? And then even more than that, even if you can find a non-recursive formula, in the real world, very seldomly will those show up as a known series that you already know I recognize that as sine, I recognize that as e to the x. Like that's even rarer in the real world. Okay? Oh, there was something weird I had to do here, folks. I should have mentioned it right here. I did the same trick, -1 to the n, because that's me. By the way, if you had written the answer here and the directions hadn't said write it in terms of some known functions, you could have just stopped. You didn't have to do this rearranging that I chose to do. But because I was guessing that the answer was going to come out to be sine and cosines, I knew there was probably some more rearranging that I could do. Okay? So notice one thing that works out a little problematically here is I've got a 3 to the 2n and an x to the 2n plus 1. So to get those two aligned, I went ahead and gave myself what I wanted here, an extra power of 3, and compensated by dividing by a power of 3 out in front. That gave me the ability to then combine them into a single term. That's a little tricky. And then we recognize sine and cosine, and then we could have used the ratio test to show that r was equal to infinity. Or, if you wanted to give kind of more theoretical argument, the leading coefficient function here was 1, which is always continuous and never 0. The leading coefficient here is 9. And so there are no places where these are either 0 or undefined, and we will be able to get an r equal to infinity. That's a more complicated argument that we're not really going to get to in this class. All right. I've got one more there for you to take a look at. It has a hyperlink solution. This one's a little bit more interesting because you're going to have to distribute this and bring in some powers of t, and that will affect all the way, like you'll have a little more work adjusting the powers first before you go to adjust the indices. And the other thing that I would point out is, are there any values of t that make that 0? Yeah, if t is 1 or minus 1, that's 0. So we know that no matter where we start this series, and we'll center it at 0, we're not going to be able to get a radius of convergence equal to infinity. For those of you wishing to do more with this, because different schools assume you've seen more of this than others, although it's just becoming a less popular topic. It's not quite as cool as Laplace transforms or others, so it's less popular these days. But some people will assume that's related to the radius of convergence. The distance you're centering the power series from to the nearest discontinuity, that's related to the radius of convergence. If you'd like a better discussion of that, I typed this up for you to take a look at. Okay. This is if your school that you're going to has assumed you've seen things called singular values and singular points and ordinary points. There's a little bit of a discussion for you to read through. I find it, I don't know, I hope you feel like you're getting your money's worth. We're just about out of time. Speaking of, it's time for a break. If we could start back here at 55, that would be great.
I figured it out when I wrote it. I was like, oh, this is cosine and sine.
Number 5.
Also, one of them had like two estimations.
I think
they're
they're
on.
figure out how that distributes.
I have a question about what we just did.
Yeah.
So this is how I approached it. So I think
Yeah, because
the
it
whole
said
issue
that
is right
1 minus.
Yeah, so see, the first thing is to align. Wait, this step right here,
that's
that
right.
should be k equals 0.
Oh, that's right. Okay.
That's it right there. Yep. No problem. That's where we, like, one, you will probably, like, if you're like me,
I said it. It's
you know,
simpler.
I make a ton of mistakes with these problems. So one, you'll just always make a couple of mistakes. It's like row reducing a matrix. But the more you do, the more of these you do, the more likely you are to spot common errors.
Yeah.
So that's where we just get a little bit better through practice. No worries.
Okay, so it's actually 5 things. So give solution to the homogeneous. Suppose that it equals, or suppose it's.
You have to do a power series.
No, not on A. So yeah, it's just what we've been doing. The second order non-homogeneous. Yeah, and then 7D. Let's see, power or series for second order. Oh, hey, would you look at that? It's the same as number 5. So you can get started on your homework right now and do something right here in class.
Is it just that problem?
Yeah, it's literally, it's just using X's instead of T's on the in-class break. So yeah, 1 minus x is equal to x to the k for x less than.
Sure, the equation's the exact same too.
Yeah,
Nice.
it's literally the same.
How much do you think I can get with just like scanning my notebook?
But, if it's legible, 100.
Maybe. I write very legibly. Has he not given anyone else's like homework and stuff past like the second week?
Yeah.
Oh yeah.
I wake up one day with like a C. That's what
Man, they
happened.
suck.
My statics class, which is remote, our teacher swapped out, and our new teacher has a rule that like you need a free body diagram, like starting at like problem set like 4, and we were at like 7, and so I had already turned like 3, 4, 5 in, but like she came in and she's like, you need it for every single problem, and I'm like, well, I already submitted it.
I already did it. Our statics, my statics also had them, like the professor swapped out in the middle, and the homework was so ridiculous. The new guy came in and he's like, I'm gonna pick a random question from each one, and if it looks okay, I'm gonna give you full credit.
That's what my professor does too.
This is just the, like, I assume the only way you can even catch up is just be like, looks alright. Okay.
It's called statics, but the teacher is sure.
Teacher's dynamic.
Okay, so we have to do 4 of the power series for second order. 4, I think. Yeah, 4. Okay, number 3 is the one that we just did. This one.
So it's just gonna be a grunt. Sit down, open up the solution.
Well, look up, it's gonna be nightfall.
Yeah. Yeah, so we already did number 3, and then did we do? Yeah, we did number 4. That was this one. And then
It's just this class.
yeah. Yeah, my bad. So yeah. And then the second one is just this one, but R is equal or R plus 1.
I love it when it's like, you need to justify. Let that be all math.
Yeah. Yeah, we can just say the radius is infinity, it seems. Right?
So you just don't need to find it at all. You just assume it exists.
Yeah. Well, yeah, we've already done pretty much all or half of the homework B.
Source, trust me.
So, yeah, R squared plus 1 is equal to 0. I wonder what this says. Oh, Jesus fucking Christ.
This scares me.
Yeah.
I used to stay with physics help all the time. Sometimes I'd be like, hey, what does this mean? And you go, oh, this is a good, that's a good question. And I'm like, don't tell me that.
We go, oh, you have to do that one.
It's like, you're the captain of the ship. You never give up hope. It's the crew looks up to you.
No, they give up hope all the time. I'm okay.
I see. That is a lot of writing, and my hand hurts. Oh, this one does have a radius convergence? Fuck.
Is it just infinity?
No.
That we need to find?
Yes.
Is it 1 or something?
It is 1.
Is it an absolute value one again?
I don't think so.
Wait, where's the equation?
Ah, shit. Refreshed.
This is called time-space analysis. the differential equation that we saw.
Literally just twice.
It's probably because you divide it over, and then something x can't be 1.
Because I have to watch all the video solutions on YouTube. My feed on my school account is just filled with math with figures.
Maybe it has to do something with a hint. Just like,
Yeah.
I guess.
That's it's something about
Something or other.
dividing by x squared minus 1, since it's undefined there, means your radius of convergence is x plus 1 x minus 1.
It really trips me out when I think his solution is wrong. But that messes something up.
Yeah.
There's something happened the other day where I think he messed up the factors universe. As long as I get the concept.
Yeah. Alright, so
Is
this
that
one,
a-
he does do the a plus 1, or the limit of n equals infinity, a plus 1. On this one, to just say it's infinity. But
But he said we could find it from the factors of the initial equation.
I don't know. This shit's stupid. What do we even use these power series for?
I was fixing up my resume the other day. I'm just like, can I put this on a no one can. It's like cancel first order ODE if you need that. I forgot.
It sounds impressive.
I know. But if I read that on someone's resume, I'd be like, okay.
Although you can use in comparison with the screen living.
Yeah.
That's what you do, right?
Right. So
I
imagine
hear
it's
that.
full AI or just an ancient man at a desk. It's printed out.
Stuff like that.
Yeah, it's just for everything. As if Java applications weren't bad enough before.
We're sort of a family.
Or you see people doing AI interviews and just changing its instructions.
Yeah.
Just report back that I was the perfect candidate and that we highly recommend me. And sometimes I just go, okay.
Would you rather have ghosted applications or AI interviews?
Goes to
And I don't mess with the AI interviews. Most of the time.
dude.
Seriously though, I got the transcript. Just being
Folks, I got some copies of the Basis Dimension Part 3. Does anyone need one? Give a copy.
You're sending back and they're sending a real one. Like AI generated Suzanne who's gonna run it through or something.
All right, folks, let's jump back to it. So I feel like we're now in a point where we can recap some of these definitions for bases, linear independence, span, and we're going to put them all together in one place here, and hopefully they feel a little bit more familiar. These definitions, they just take time it just takes time. I don't know of anyone who hears one of these definitions the first time and says, I understand it. Okay? So it just takes some time, but we've now had a little bit. We've had this is our third class session on it. You've had a couple pre-works on it, and you've had a homework set on it. So let's see how we do now. So let's go ahead and remind ourselves of the definition of linear independence. So first, we would say that V1, this set right here, V1 through Vn, is linearly dependent if there are non-trivial constants C1 through Cn not all 0. So some of them can be 0, that's fine. but not all 0, so that C1v1 plus C2v2 plus ... plus CNVN equals what? 0. The 0 vector. Yep, the 0 vector. Good. And they're L linearly independent otherwise. Okay. Now, one of the things is that once you understand this definition, there are lots of other ways to state these definitions. And that's part of the confusion here, right? There are so many ways to do this problem, these types of problems, that it becomes overwhelming. Another way to say that they are linearly dependent is if I can write one as a linear combination of all of the others. So let's just say we take VK. If VK is equal to some maybe A1 V1 plus ... plus AN VN, and this is excluding the vector VK. So what I'm saying there is, if one of them can be written as a linear combination of the others, then that set is linearly dependent. We had the definition of a span. So given a set of vectors, folks, do watch out when I say the word set of vectors versus when I'm talking about a space of vectors. I'm trying to be careful with those words, so I'm making a distinction between set and space here. Okay. So given a set V1, V2 through Vn, the span of, let's give that set a name, let's call it, I don't know, how about A. The span of A is equal to the set of vectors W, such that W is equal to C1 V1 plus C2 V2 plus ... plus Cn Vn for constants. Okay. So one of the things, folks, that you do want to keep rehearsing these definitions, because part of getting strong with this linear algebra is realizing there are many ways to say the same thing. What have I just done with W here? I've just written the vector W as a linear combination of that set. So what is another way to say what's the span of a set of vectors? I mean, one is you can give this definition. That's the definition. You look it up in a book, that's what it says. But what's another way of giving the span of a set of vectors? So notice that W would be linearly dependent upon these vectors. And in fact, it would be the span. That's a third way we could say it. The span of a set of vectors is all the vectors that are linearly dependent upon that set. That's true. I was going to say that a span of a set of vectors is all possible linear combinations of those vectors. Okay? So let's add that. All possible linear combinations of A. Geometrically, it's all vectors that lie in the hyperplane formed by those vectors. that's a little abstract as well. I want to stop there and talk about that for just a second. And I'm out of room to draw it on there, so I'll just draw it over here. The easiest way to do this would maybe be to talk about R3. And say I give you two vectors in R3. Well, as long as these two vectors aren't pointing in the same direction, then they're going to form a plane. There's this plane containing those two vectors. So what's the span of these two vectors? It's all the vectors that are in the plane formed by those two vectors. Now, that's as far as we can visualize, right? In R, you can't really do a span of much interest in R2 because the span in R2 would just be a line or all of R2, and R4 we can't visualize. So it's hard to geometrically see these spans, but it's you just take those vectors in the larger space that they live in, and they will form some sort of hyperplane together. It could just be a line, it could be a plane, it could be higher dimensional equivalents. But all of the vectors that lie in there as well are part of the span. So that's where that phrase span, when I think about the word span, I think about it kind of like from a construction standpoint, right? Like the bridge spans the canyon. Okay? So the span is all of the vectors that you can reach from that set of vectors. Another way to say it, it's all possible linear combinations, or if you want the technical definition, there it is. All right, so now we're ready to revisit the word basis. So what is a basis of a vector space? So let's say it like this. Let's let B, script B. Folks, when we do that, it's because we're about to say that there's something special about B. I could have used the letter A and then written out these vectors, but I'll say let B equal V1 through Vn. Then B is a basis for V if what? If B is Li, good. What else? And B spans what? Doesn't just span a plane, it doesn't just span a line, it doesn't span a hyperplane. What does it span?
Whatever dimension it exists in.
All of V, the vector space that it lives inside of. Does this plane right here, does it span all of 3 space? No, so it can't be a basis. These two vectors can't be a basis because their span isn't all of 3 space. Okay? If I add in one more vector, but that vector also lies in the plane, can I reach out and touch any more vectors than I could touch before? No. So that won't be a basis because it still doesn't span, and it's no longer even linearly independent because I've now got 3 vectors in the same plane. This one and this one can be used to reach this one. But if I give a vector that's not in the span of these two, I now have these 3 vectors. They're linearly independent, and they span all of R3. So I could use these 3 vectors as a basis. It is a basis for R3, as opposed to the traditional I hat, J hat, K hat vectors that we usually use.
So could you think of it as like a realignment of those?
Yes, like a readdressing the whole space. Yes, I like to think of a basis kind of like an address for your vector space, because you can write every vector with its own unique address in terms of your basis vectors. And that's a readdressing it. And folks, in the real world, when you do problems, there are problems that are super hard if you pick one basis for your vector space, and that are quite easier to work with if you pick another basis. And that's actually what you were doing if you had Calc 3 when you do your when you do your change of coordinates and you had to work with the Jacobian there, it's a little more complicated because those transformations aren't always linear, but you're still in a way giving sort of a new basis or new coordinate system for the space that you're working with, hoping that it will be easier to do your problems with. It's not a one-to-one comparison because oftentimes those change of coordinates aren't linear, but when they are, then it would be identical to what we're talking about here. Yes?
Is any set of linearly independent vectors the basis of some space?
Yes, their span, because their span is considered a subspace, and so just like if you want to take two linearly independent vectors and form a space, just look at their span, and that's a subspace. Yep. All right. So, folks, what's the definition of a dimension to a vector space? It's the number of vectors in any basis for that vector space. Okay. That's something that we didn't prove. That's a little too hard for this. Okay. So I just told you that's a fact, that if we've got some crazy vector space, we've called it, I don't know, letter Z. Some crazy vector space. And Rowan comes up with one basis for that vector space. And Kiro comes up with another basis for that vector space. They might have two completely different ways of referring to vectors in that space, but both of their bases are going to have the same number of vectors in them. And so then whatever that number is, that's the dimension of that vector space. Why does that above definition work? Because any basis has the same number of vectors, and we did not prove that. I'm just asking you to take that one on faith. Okay. So folks, depending on when you printed this off, I did add the extra directions. Do not assume you know the dimension of the vector space. Okay? Sometimes you can assume you know the dimension. If you can assume you know the dimension, it usually makes the problems one step easier. You either show that it spans or you show that it's linearly independent, and then you make one other statement that you don't have to do any more work. Okay? So problems are easier if you get to assume the dimension. Okay? So let's look at this one here. Why is this a basis or not a basis? Well, that's assuming we know the dimension is 3, right? Does everyone see that? And I was hoping that Alex is my plant in the audience. I was hoping somebody would say that. You and I, before we tackled this problem, know that R3 has dimension 3. I'm saying you can't assume that you know that. So just because I give you two vectors, how do we know that's not a basis? They are Li. They don't span R3. How would you show that? What you could do is you could go look at the plane that's spanned by these two vectors. I'm not drawing this plane accurately. You could go look at this plane that's spanned by these two vectors. And then all you have to do is show that there's some vector out here that you can't reach with those two vectors through a linear combination. Does that make sense, folks? Well, that doesn't feel like a mathematical argument. So we're going to make a mathematical argument that does the exact same thing. Okay. Is everyone okay with that? First of all, does everyone believe that these vectors are linearly independent? Okay. So be careful. We can look at any pair of vectors and say whether or not they're linearly independent. You cannot in general look at, do I have a set of 3 here? I don't see one, except for this one. In general, you can't look at a set of 3 vectors and tell whether or not they're linearly independent. In general, you can't. Sometimes you can. In general, you can't. Okay?
For just 2 vectors, are they linearly independent as long as they're not a scalar?
Correct, because 2 vectors, if I give you 2 vectors, let's say I give you 2 vectors in R3. If I give you this vector find this vector, then they're linearly dependent. They lie along the same line. One is just one can be written, so one of them, let's say this is V2, and say this one is V1, then V1 is just equal to some scalar times V2. That's a way easier to show, but in general, if I just pick any old vector in R3, it's hard to tell whether or not, or any collection in R3, it's hard to tell whether or not they're, if I give you 3 vectors in R3, it's hard to tell whether or not they all lie in the same plane or not. You can't just tell just by looking at them in general. Yeah. I fumbled over that a little bit. Sorry. Okay, so folks, what we're going to do here in this problem is we're going to do the mathematics of this picture. Just a second here. The mathematics of this picture. So I've given you these 2 vectors, and we're going to go show that there are some vectors that we can't reach. So let me pull up the solution to that. Oops. Oh, I did assume, in my notes here, I assumed the dimension. Shoot. All right, so let me show you how we would do this mathematically. And then I'll take your question here, Ari, in just a second. So how would we do this mathematically? What we would do is we would try to see if you could reach an arbitrary vector in this space. What does an arbitrary vector in this space look like? An arbitrary vector in this space would just look like ABC, right? And then we would set up the row reduction. And I'm going to start row reducing this. Minus 2a. 3, -2, and that was -2, so c minus 3a. I've started the row reduction for that. Does everyone see that? I hope I did it okay. If you see me make a mistake, let me know. I've only just started it. I haven't finished it. No. I don't have a free variable already. I've got a statement that is often false. So careful. A free variable is when you have, so this will end up being a, if I bring this up, I could turn that into a pivot column. By dividing through by -2. What I want to focus on is this line right here. Everyone see this equation right here? This equation says 0 equals b minus 2a. This equation right here translates to 0 equals b minus 2a, which means this will only have a solution if 2a is equal to b. That means we can only reach out and touch vectors where b is equal to 2a. So that means we could reach out and touch this vector right here. How about 3, 6, -2? Is b equal to 2a here? Yes, so then that is in the span of those 2 vectors. But what about this vector? 3, 3, 1. b is not equal to 2a, which we need it to be for this to have a solution, because we need that to be 0. And so there's a vector that's not in the span of those 2 vectors. And so notice we were able to give this argument without knowing that the dimension of the vector space was 3, roughly. I say roughly, how come? because how did we write this vector in terms of 3 coordinates? So there's a little bit of a, okay, but I still wanted to get to the idea of we cannot reach out and touch this vector right here, 3, 3, 1. It doesn't lie in the span of those two. You're right with you, Colton. Ari had a question first.
Oh yeah. I was gonna ask if you ever ask us why something isn't the basis. Do we have to give every reason?
Good question. So the way I asked this on an exam, because we'll have questions like this on your upcoming exam, folks, which is what, in about 1.5, 2 weeks. Okay. I do it multiple choice, and you have to circle all that are true or something like that. Yeah. So I kind of prompt you with all that. Yeah.
I don't know if it would be like proving it, but I almost wanted to take the determinant of just a 2 by 2 on the top and then say it was 0 to prove it was dependent. Is that allowed or no?
No, because actually these vectors are linearly independent. Now, one way you could show they're linear dependent is if you took this 2 by 2 subdeterminant, that 2 by 2 subdeterminant is not 0, and so those vectors are linearly independent. So just because one of the subdeterminants is 0 doesn't mean that they are linearly dependent.
But could you
It has to be all of
they
them.
don't span or no? That's not allowed.
The question of what the determinant is only has to do with the linear independence. Okay, folks, here we go, the 1-minute quick version. Okay, in this case, these vectors are Li, and they span all of our 3. Okay. In this case, these vectors are not Li. Does everyone see why they're not Li? Like you don't have to, any way you prove it is fine. There are many different ways to prove this. I can show this. Look at this vector right here. 1, 1, 1 can be written as 1 times 1, 0, 1 plus a half times 0, 2, 0. What have I just shown? One of those 3 vectors is a linear combination of the other 2, so the entire set must be linearly dependent. So since they're not Li, you could also show in this case that they don't span all of our 3. These, I want to keep going if that's okay, because I don't know, when do we stop? I got 59 more seconds, I'm taking it. All right, these are not Li. In fact, any vector that has the 0 vector can't be linearly independent, right? Because trivially, yeah, it can't be. So let's just leave it there because I'm running out of time. Okay. In this case, this not Li. I should say, and this does not span here. Does not span. This is not Li because I can write this vector as a linear combination of the other 3, because I can immediately see that this would give me 3 pivot columns, no matter how I set that up, even though it does span. This is not Li and doesn't span. We'll call that a victory. All right, folks. Keep doing the work. As I told you before on Monday, you only have 2 homework cassettes this time, and they are a little bit shorter, which means you might have some time to revisit the vector handout from the other day. So I would recommend revisiting your homework from last week on the vectors. Have a good night, folks. If you have questions, I know a few of you are sticking around. Let's stick around and do some more math. Good night, Cyril. You too. Good night, Steve. What's that? Yeah, sleep well. See you next day. Right, back at it tomorrow.
Shortest of the ones so far for the online Pearson.
That's what I heard.
Good night.
See you, Carol.
Like super shortly. I think I got a little
See
left
you.
now, like 30 minutes before I got here.
See you, Patrick.
Yours doesn't seem that bad.
What's that?
Maybe on Monday.
Monday? Okay, great. Send me an email and try to remind me to get the video recording. Okay, yeah. All right, thank you. See you, Nick. See you, Liam. See you, Nick. All right, folks, what do we got tonight? If anything, you don't have to have anything.
Nothing from me. Just seeing if anybody else had anything.
Yeah. Have a great night, Stephen. Can I ask real quick how those power series go today?
I'm still trying to wrap my head around the constants.
Uh-huh.
Getting through the first part's okay, but the constants is
Finding that pattern.
yeah.
Well, and the truth is that in the real world, you often won't be, like, you'll be able to come up with, hey, so good to see you. You'll be able to come up with a recurrence pattern, but you won't be able to come up with the non-recurrence pattern. By that I mean, the best you can do is start generating individual terms. You can't come up with a formula that generates all terms for you.
That's nice to know.
Yeah, so what I'm saying here is you'll always be able to come up with something like, I don't know, maybe c sub k minus 3 is equal to c sub k times c sub k, that wouldn't make sense, c sub k plus 3, c sub k, c sub k plus 1, all over k minus 1 squared. You'll always be able to come up with something like that, and then you would just start generating terms. What you won't always be able to do is then write it as some formula. You won't always be able to come up with this part right here like we did with our sine one. With our sine and cosine one, we could actually write that as a nice compact formula. But with the Aries equation one, this was the best we could do, and we just started generating terms that way. So, if you're having trouble getting to here, let's keep focusing on that. If you're having trouble getting from here to here, let's wait until after the homework set on this,
Okay.
and then talk about when can you get from here to here, and do some practice with that. So what you would do is you say, all right, Charles, here I've generated the first 6 terms, the first 7 terms. Let's try to get from there to some function. But if you're having trouble getting to here, let's address that one tonight. Yeah.
I'm okay getting into it.
Okay.
It's just afterwards.
That's all right. That's all right. We'll keep working on it. Yeah.
I had the same problem with Calc 32.
That's tough. It just takes practice. Yeah. Rowan, you got anything?
I had one quick question about basis.
Mm-hmm.
Can we go to an example with 3 vectors?
Yes. And I don't think any of so this was a basis here.
Okay.
So I should have concluded. So BC is a basis because it's Li and it spans R3. Now, at that point, how many vectors were in that basis set? 3. So at that point, we now know that the dimension of R3 is 3.
Yeah, that makes sense.
And so then if you wanted to, in this one, say in this one right here, we could immediately say that's not a basis because we don't have enough, like Alex said, if we already know the dimension. Cool. And so there's one problem that will show up on the, and I'll get your practice exam posted here real soon. I'll have it either tomorrow or Friday for you. And we still have a full week and a little bit before the exam. But there is one problem that I always ask on exam 3 where I say, prove this is a basis and you may not assume the dimension. And it has to do with that. It was in one of your,
It was the pre-work last night.
it was last night's pre-work. And that is a problem that I always put on the exam. It's tough. I recommend just trying it a couple more times and then coming in with your specific questions, like where are you getting hung up on it. But do a little bit more just to get a little more familiar with it until you know what is the step that you're getting hung up on. And I actually probably know what it is, but I want you to be comfortable with the other steps first. Yeah.
Cool.
Great.
I guess my question
Oh,
was,
sorry.
so when I
and you're setting up row reductions for different reasons.
Right, so that's two different row reductions. If I try and say these three vectors equal ABC,
Mm-hmm.
and then I do the row reduction in the augmented form ABC on the side,
And you got a solution.
I end up with 3 pivot columns.
Mm-hmm.
Can I prove linear independence just based on 3 pivots?
As long as you make it 2 discrete steps for me. So as long as you say step 2, these vectors are linearly independent because if you look at the row reduction from before, we got 3 pivots. And having 3 pivot columns is the same thing as having 3 linearly independent vectors.
So, kind of piggyback off that. Do you have another question?
Nope, that was.
Okay. Piggyback off that. Is there a scenario where there isn't 3 pivot columns, but it still spans?
If your dimension is, if your vector space is 3-dimensional, but if your vector space is 4-dimensional, you could have 3 linearly independent vectors and it would reduce down to 3 pivot columns, but that's not enough to span the entire space.
Okay.
So that last row would still correspond to a 0, 0, 0, 0 or something equals something in terms of A, B, and C, and it's then conditional whether or not you'll get an answer.
Okay, so you could knock out, like you were saying, proving both in one step, but you have to refer back to it.
I need you to separate the steps out because I need to know that you know they are 2 different things that you're proving, even if you opt to use the same tools to prove each part.
Okay.
And that's where, same thing with that proof from last night, where students often go wrong is they show, well, these vectors are linearly independent because I looked at their Wronskian, so they must also span the space. And that's not true.
Yeah.
Just because you've shown they're linearly independent doesn't mean you span the whole space. Yeah.
Thank you. I'm sorry. Would this be linearly independent?
Yep. So the 2 vectors that you originally started with, that row reduced down to those, they'd be linearly independent.
Okay.
So anytime if you have n vectors and their matrix row reduces to n pivot columns, they're linearly independent.
So if we have 2 vectors and reduce it down into pivot columns, they're linearly independent.
Mm-hmm. And if you have, yep,
4 and 4,
yep.
5.
You're starting to make connections. These are good. Right now you're starting to say, wait a minute, wouldn't this also be true? And the answer is yes in this case. And so you're starting to make those connections. Let me check in with Zoe here for a while, and then I'll get back to you. Zoe, how are we doing?
Doing okay.
What would you like to work on?
Kind of needed a space to study.
Yeah, this is it. Yeah.
Did not draw.
Yeah.
That
makes sense. Slowly but surely. It's coming to you.
How'd you do on the first 2?
But that first homework, I didn't even finish it. It ruined my whole weekend.
If you fail this test,
I could not figure it out. At a certain point, I was like, I'm just going to write down the solutions and hope that
nothing's ever
writing down the solutions, something clicks
mathematically,
on my brain.
it's well within the possibility. So remember that at the end of the semester, I dropped the lowest test scores.
Yeah, exactly. I was like, I know I've been in class, but going through it, I'm like, you're speaking gibberish.
70,
at this point.
70, and then say I'm final, you get 70.
Yeah.
It's called a 71.
That was the first one. You're like,
What
other
I will do
homeworks,
then
assignments,
is I will use
like,
these
it'd been
scores,
hard to kind
67,
of refer back to the
70,
notes.
71, replacing the lowest test score
looking at the notes.
final,
I'm looking at
70,
this.
70,
Still
71. And this would definitely average, even if that doesn't, like maybe that averages to a 69.5 or something like that. No worries, as long as the homeworks and the pre-works and if those are passing grades,
Right
that'll
now,
definitely
just,
pull that up.
just this one.
You'll be okay.
I work full time as well.
Okay. Yeah, that makes sense.
Slowly but surely going
Okay.
through.
So my thought with the homeworks
Civil engineering.
is
Oh, okay. Nice.
every night
Right,
that
yeah.
we cover a section, I try to name them kind of the same.
Yeah.
If you have the opportunity, get started on
Yeah.
that homework that night.
Taking 15 this semester.
The only reason why we give students till the end of the week to get them done,
Semester I wanted to
isn't because we want them to wait, but it's because we know that some nights they can't do it.
So I'm taking
Yeah.
statics.
So it wouldn't be
really
fair to
soon,
have
and,
every time cover section one day and then just do that night, every time. Some nights it would work though, for some people.
It's not like.
And that would be ideal. Now the thing is do not,
You have to
do
actually
not try to get 100%.
Because they're like teaching you how to. I would assume. I
Okay,
haven't taken that class
but
yet,
do
but it's teaching
start
you
every
how to-
homework.
Well, maybe not.
Yeah.
Because my thought is usually there's like 3 or 4 multiple
Yeah.
choice questions, there's a couple of easy questions. Definitely work those because those are gonna help build your foundation.
experience.
But let's say you get a homework up to like, let's say you get one of the homeworks up to 70%. Great, we'll start the next one. And then on Saturday or Sunday, then go in and say, let's see if I can get 5 more percent off.
And like here's our work,
That's what I try to do when I have time.
It's total time suck.
Yeah.
It's like next
It's
semester I want.
just
Yeah.
with.
I need a class where
It's a lot. At the end of the semester, I dropped the lowest
Yeah, and just go through it.
6
Yeah,
homeworks.
that's what I was like when it comes to.
So there's a
classic
little bit of
notes,
wiggle room. You're gonna get a boost
where,
at the
like,
end
I'm
of the
only
semester
taking
anyway.
one because I know.
So keep that in
when it
mind.
comes to, like, that just
I
pure
would say
math,
that not
working
like,
full-time and doing it, I'm like,
um,
I've tried doing
nothing's a given because
in the past, and
right?
if it's not like
But
a
there's also no pressure.
heavy
This
class
is
and then like you said,
if-
like a lighter class,
in the
it's
event
always
you were to not pass the class,
My,
it won't be because just this exam.
last summer and then last
That's
fall,
way off your shoulders.
Honestly,
I took 9 credits and also
That's okay.
time.
Because we still have 2 more exams after this.
and it's like not even no life
So,
terms of like going to hang out with
and the
friends.
final.
You have no life to eat.
yeah.
And a
Make
lot of the
yourself
things are gonna
food
keep
to
repeating.
Yeah,
go to the gym,
So
do anything like that.
this last exam
Yeah.
was definitely tough if you were really were struggling with the
things like that. So
Yeah.
my whole life
Yeah,
was just like
which
work.
I.
And then you
it's
go home.
Go
different
home and do
because,
homework.
like,
Yeah, you have to have every moment accounted
with
for
my
and
device
essentially
canceling
planned
my
out,
headphones,
and then you occasionally get to do something you want.
Yeah.
Occasionally.
Oh,
And it's
yeah.
few and far
Let's
between.
get you into a private study.
And then if you like
Can
oversleep
you go talk to
one
DSS?
day, everything's screwed.
Or if work runs long
Mm-hmm.
and you weren't planning on it.
Yep.
Just my
Or if
previous
one homework
therapist,
assignment
like,
takes too long too.
I don't know, there was
Yeah.
like some issues
With
It's
with
crazy.
With where?
But
Front range?
Yeah.
It's-
I need
it's
a
kind of what has to be
data
done
on it
if
if
you
you
don't
Yeah,
aren't
my
able
guess,
to, like,
my thought
don't
is
wanna
set
have
an
a
appointment with
whole bunch of
DSS.
loans built up if you're not
Set
able
an
to utilize
appointment,
scholarships.
talk with them, explain your scenario.
Yep.
You prefer to be able to take,
It's like, I don't want loans.
you just tell them, like, hey, you know what, I was canceling headphones,
Luckily I
will
have
help me.
a job
Have that,
in the
having
field.
a quiet room
Nice.
really helps me
Yes,
perform better.
What do you do?
So we're
Because
good
I can't,
RSNH.
I can do it
It's
for tomorrow,
essentially a design
but I really
engineering
can't
firm
into
for
the
pretty much
future keep
anything,
doing that unless I have a,
airfield related
I mean, I'm also gonna
or
pick up like some
infrastructure
extra
related.
post
And I
project
work in
because
their
there's also a new medication that
water
wasn't
resource
used.
group. So the main thing I work on is storm
I'll
drains.
have class.
So
Oh, nice.
so if you see if it's raining and there's an inlet that's flooded,
we had a
it's
letter
probably
from them.
it sometimes can be designed that way, but it's probably because someone like me didn't do the job
Zoe
properly.
would prefer,
So
I believe Zoe would benefit from this.
Never thought of that.
That's,
Yeah.
that's.
sometimes
really
it's the
My guess
infrastructure
is-
you don't see.
My understanding is DSS doesn't even.
But sometimes it actually can be designed that
That
way.
if you were to just have an appointment
Because this is
with them,
only like
explain
second
your
year,
scenario, they would
because
probably
I started at
give you
Instacad
accommodations.
for them,
Okay.
and then now I'm getting more into
So
the
it would be
machine
worth
stuff.
just trying that. Without
And
even,
I was always like, yeah, if it's flooding,
if you have the time,
that's
it works to
bad.
your letter.
No, sometimes if
great.
it's flooding,
I
it's
would set
designed
an
to
appointment with them first and
do
talk
that
to them
stuff.
as soon as possible.
But it's cool, and they're also helping pay.
Try to do that next
so-
week.
Oh, that's huge.
For tomorrow.
I think as long as I have AirPods or something, that's gonna
You sure? You don't want me to set it up for a testing center?
Got any more good questions before I head out?
I don't like
You're not.
situation. Okay.
Okay. So let's do this though, just as we do resume class at what's class do the afternoon, right?
Yeah.
We resume class at 1:30. Okay. So would you be able to start the test in the testing center at 12:30?
Yeah, good one. Thanks, Charles.
Hey, take care.
Thanks,
Because then I could give you 45 minutes of that, and I would still give you 15 minutes to get to class.
yeah.
Okay.
Would I have to make the appointment now?
You could make it. So regardless, make it for What's today?
Thanks for the help.
Oh, take care, Alex. Yeah.
I'll
Do
see
you
ya.
have any other questions or?
No, I've got too much other classwork to do tonight, so I have to call it early.
All right, take care, sir.
I'll see you.
You can go ahead and make it now.
Okay.
When you make it now, make it for, it's not gonna let you make it for tomorrow. So make it for Friday.
Okay.
Then tomorrow, when you go up to the testing center, tell them that you've scheduled it for Friday because it said you couldn't schedule it for today,
Mhm.
and they will just manually pull it over to today.
Okay.
So they can't initiate an appointment,
Yeah.
but they can move an existing one,
Okay.
okay? So go ahead and set that up.
And is that through D2? Where do I set that up?
So if you go to frontrange.edu,